All right, welcome to lecture 14a. We're going to derive the momentum equation here. 14b, we're gonna apply the momentum equation to a problem, and then in the next lecture, 15, we'll start solving problems with it. This is going to be another one of our tools that's going to kind of show up all over the place. So to derive it, I want you to recall the Reynolds transport theorem, and the Reynolds transport theorem has to do with some b. Okay, and we're going to look at how that, and then a lowercase b, which is b per unit mass. And so basically we have some b, some stuff. Okay, it could be cows. I've heard it, there was a professor at the University of Texas who used to call this be cows. It's the number of cows, the change in cows per time within a system. Okay, and we're going to say that well, we've got a control volume. This is the number of cows within the control volume, how that changes. And then this will be, it depends on how many cows enter and leave that control volume. But we're not worried about cows here. We're worried about momentum. Okay, so B in this case is going to be momentum. And if you remember momentum from undergrad or basic physics or whatever, it's mass times volume. Times velocity. Okay, and with the velocity being a vector. Okay, lowercase b, okay, if you remember from the Reynolds transport theorem when we talked about that, is momentum per mass. Okay, so if we take momentum and we divide by mass, we just get the velocity. Okay, now the last simplification we're going to do to this Reynolds transport theorem in order to arrive at kind of a momentum equation, or at least get in that direction, is we're going to use so dB cis dt equals, okay, and this is a version, okay, so that's the change in momentum with respect to time, because capital B is momentum, and this is another version of Newton's second law. Okay, so one of the ways that you can write usually we write Newton's second law as the sum of the force equals mass times acceleration. This is another way that you can write it. We don't normally do this, at least not for basic physics, but this is another way to do it. Okay, so Newton's second law. Okay, so if we plug all these things up into the Reynolds transport theorem, well, let's see. So dB cis we're going to place as sum of forces, okay, equals d by dt, integral of the control volume. Lowercase b becomes the the velocity, rho dv, plus over the control surface, the integral over the control surface of v rho v dot dA. Okay. Now, right now you're thinking, hopefully, or at least some of you are thinking, why didn't I just square those v's? Okay, and there's actually a very good reason for that, and that is that dot product. So what that dot product tells you is that you cannot square it because one of those v's has to be dotted with that dA before you can move forward with it. Okay, so what we're going to do at this point is we're going to start to kind of simplify this. And the first thing that I'm going to do is in this class, so if ever you work in an unsteady system, you won't be able to make this assumption, but for this class, we're going to always work in a steady system. Okay, so if you guys go on into fluids and you start working on tides or any sort of unsteady system, you're not going to be able to get rid of that term. But for us, we can. So I can say the sum of the forces equals over the control surface of v rho v dot dA. Okay, now this is an interesting equation. This is the linear momentum equation. This is the steady linear momentum, okay, equations. Okay, now I'm going to underline that S because this is three equations. This is in the x direction, the y direction, and the z direction. Okay, now what I'm going to do for this class is I'm going to make this a little bit simpler, and I'm going to show you why. And so normally what happens, let's suppose we had some sort of pipe or something. If we had a pipe, okay, and I would draw a control volume, and I would say, well, okay, here's my control volume right here. Okay, and the way this dot product works, okay, the control volume is just the fluid, And the way the control volume works is we'll call this V1 and we'll call this V2. Okay, and we would also have an area, right? And I'm going to draw those areas in green. So here's a cross-sectional area for that opening. Here's cross-sectional area for that opening. And the area is going in this direction because the areas always point out, A1 and A2. Okay, so what happens here is based on that, when I do V2 dot A2, okay, I end up getting, because these two are in the same direction, I end up getting Q2 with a positive sign. And over here, I end up with V1, A1. I end up getting a negative Q1 because the A1 and the V1 are in opposite directions. Okay? So what ends up happening up here is if I take this thing and I move it on down here, you see this is the out right here, and this is the in. And all the ends end up having negative sign, and all the outs end up having positive signs. So what I'm going to do here is I'm going to break this up like this. The sum of the forces equals, okay, this V dot dA included with this integral, that's just Q. Okay, so what I'm going to do is I'm going to say V rho Q, okay, and we're going to do the outs, and those are positive. And then I'm going to subtract, because the negative ones, sum of the ends of V rho Q, like that. Okay? So by doing that, what I've done is I don't have to worry about this dot product anymore. Okay? I don't want to have to deal with this. Okay? So I'm going to rearrange this, and I'm going to say the sum of the forces equals, oh, no, I don't want equals. Okay, plus the sum in of V rho Q equals the sum of the outs V rho Q. Okay? And so this is how we're going to do it for this class for the most part. Okay? And the way I think about this is because it's steady, there's no accumulation of momentum. So basically we have the forces, which is kind of a force. It can either give momentum or it can take momentum away, depending on whether or not the force is in the direction of the flow or against the direction of the flow. And this is the flow in, the momentum flux in, and this is the momentum flux out. Okay, you might say, well, how is that a momentum flux? Okay, well, V, that's a momentum. So this is, let's do this right. Okay, so rho Q. Okay, rho, this is mass per volume times this is volume per time. Okay, so those volumes cancel, and I get mass per time. Now I'm going to multiply that times velocity. So now I've got velocity times mass, so this is momentum per time that is crossing into the control volume. Okay, because remember, this in implies that it is crossing the control volume. So this is my control volume. Okay, basically, the only way the momentum in here can change, well, there's a few ways it can change, but one of the ways it can change is that momentum can flow in. Okay, another way that it can change is that momentum can flow out. So something could be moving out this way, and it could be taking momentum with it. Okay, the last thing that could happen to it is there could be forces on that container. So there could be, like, if this were a lake, there might be wind acting over the top. Okay, there might be friction along these edges, causing it to lose momentum. There might be, there might be something pushing on this fluid for some reason, okay, or pulling on it. It's kind of hard to pull on a fluid. But that sort of thing, okay? There could be pressures on these sides pushing, and there's never pressures pulling, okay? And that's ultimately how this all works together. So in the end, what we're going to do is I'm just going to recopy down a nice clean version of this. V rho Q equals the sum of the outs, V rho Q. And then we're going to write this in, and because this is actually three equations, we'll write out those three equations. And so if we do so, we get these three equations, okay? Noting that the Vx, the Vy, the only things that are kind of like vector quantities are this velocity. So Q is a scalar, right? So all the Q is doing is carrying the momentum in or out, okay? So how much momentum is it carrying in or out? Well, that depends on how much velocity we have in the x direction, okay? And so that's how this works, okay? And it's going to be a little confusing until you see a problem working, but we're going to work an example for the rest of today, and then we will in part B, and then next class we'll work an example and we'll kind of add in some Bernoulli and some other things, okay? So get ready for part B, and I hope that was not too confusing, but this is all you really need from this. Okay, thank you, bye. So that is